Chapter 2, Wholes and Parts. A quote from Isaac Asimov. It is the nature of the mind that makes individuals kin, and the differences in the shape, form, or manner of the material atoms out of whose intricate relationships that mind is built are altogether trivial. 2.1 Components and Connections. We saw that builders' skill could be reduced to the simpler skills of get and put. Then we saw how these, in turn, could be made of even simpler ones. Get merely needs to move the hand to grasp the block that find just found. Put only has to move the hand so that it puts that block upon the tower top. So it might appear that all of builders' functions have been reduced to things that simpler parts can do. But something important has been left out. Builder is not merely a collection of parts like find, get, put, and all the rest. For builder would not work at all unless those agents were linked to one another by a suitable network of interconnections. Agents by themselves: put, begin, add, end, see, find, get, move, grasp, release, find, place. Agents in a bureaucracy, and we see a tree, an illustration with a tree structure with builder at the top, and then nested below it begin, add, end, find, place, find, get, put, etc. all below it, down to see, grasp, move, release. Could you predict what builder does from knowing just that left hand list? This is the agents by themselves list. Of course not. You must also know which agents work for which. Similarly, you couldn't predict what would happen in a human community from knowing only what each separate individual can do. You must also know how they are organized. That is, who talks to whom. And it's the same for understanding any large and complex thing. First, we must know how each separate part works. Second, we must know how each part interacts with those to which it is connected. And third, we have to understand how all these local interactions combine to accomplish what the system does, as seen from the outside. In the case of the human brain, it will take a long time to solve these three kinds of problems. First, we will have to understand how brain cells work. This will be difficult because there are hundreds of different types of brain cells. Then we'll have to understand how the cells of each type interact with the other types of cells to which they connect. There could be thousands of these different kinds of interactions. Then finally comes the hardest part. We'll have to understand how our billions of brain cells are organized into societies. To do this, we'll need to develop many new theories about and organizational concepts. The more we can find out about how our brains evolved from those of simpler animals, the easier that task will be. 2.2 Novelists and Reductionists. It's always best when mysteries can be explained in terms of things we know. But when we find this hard to do, we must decide whether to keep trying to make old theories work or to discard them and try new ones. I think this is partly a matter of personality. Let's call reductionists those people who prefer to build on old ideas, and novelists the ones who like to champion new hypotheses. Reductionists are usually right, at least at science's cautious core, where novelties rarely survive for long. Outside that realm, though, novelists reign, since older ideas have had more time to show their flaws. It really is amazing how certain sciences depend upon so few kinds of explanations. The science of physics can now explain virtually everything we see, at least in principle, in terms of how a very few kinds of particles and force fields interact. Over the past few centuries, reductionism has been remarkably successful. What makes it possible to describe so much of the world in terms of so few basic rules? No one knows. Many scientists look on chemistry and physics as ideal models of what psychology should be like. After all, the atoms in the brain are subject to all the same all-inclusive physical laws that govern every other form of matter. Then, can we also explain what our brains actually do entirely in terms of those same basic principles? The answer is no, simply because even if we understood how each of our billions of brain cells work separately, this would not tell us how the brain works as an agency. The laws of thought depend not only upon the properties of those brain cells, but also on how they are connected. And these connections are established not by the basic general laws of physics, but by the particular arrangements of the millions of bits of information in our inherited genes. To be sure, general laws apply to everything, but for that very reason, they can rarely explain anything in particular. Does this mean that psychology must reject the laws of physics and find its own? Of course not. It is not a matter of different laws, but of additional kinds of theories and principles that operate at higher levels of organization. Our ideas of how Builder works as an agency need not and must not conflict with our knowledge of how Builder's lower level agents work. Each higher level of description must add to our knowledge about lower levels rather than replace it. We'll return to the idea of level at many places in this book. Will psychology ever resemble any of the sciences that have successfully reduced their subjects to only a very few principles? That depends on what you mean by few. In physics, we're used to explanations in terms of perhaps a dozen basic principles. For psychology, our explanations will have to combine hundreds of smaller theories. To physicists, that number may seem too large. To humanists, it may seem too small. 2.3. Parts and wholes. We're often told that certain wholes are more than the sum of their parts. We hear this expressed with different words like holistic or gestalt, whose academic tones suggest that they refer to clear and definite ideas. But I suspect the actual function of such terms is to anesthetize a sense of ignorance. We say gestalt when things combine to act in ways we can't explain. Holistic when we're caught off guard by unexpected happenings and realize we understand less than we thought we did. For example, consider the two sets of questions below, the first subjective, the second objective. What makes a drawing more than just its separate lines? How is a personality more than a set of traits? In what way is a culture more than a mere collection of customs? What makes a tower more than separate blocks? Why is a chain more than its various links? How is a wall more than a set of bricks? Why do the objective questions seem less mysterious? Because we have good ways to answer them in terms of how things interact. To explain how walls and towers work, we just point out how every block is held in place by its neighbours and by gravity. To explain why chain links cannot come apart, we can demonstrate how each would get in its neighbour's way. These explanations seem almost self-evident to adults. However, they did not seem so simple when we were children, and it took each of us several years to learn how real-world objects interact. For example, to prevent any two objects from ever being in the same place, we regard such knowledge as obvious, only because we cannot remember how hard it was to learn. Why does it seem so much harder to explain our reactions to drawings, personalities, and cultural traditions? Many people assume that those subjective kinds of questions are impossible to answer because they involve our minds. But that doesn't mean they can't be answered. It only means that we must first know more about our minds. Subjective reactions are also based on how things interact. The difference is that here we are not concerned with objects in the world outside, but with processes inside our brains. In other words, those questions about arts, traits, and styles of life are actually quite technical. They ask us to explain what happens among the agents in our minds. But this is a subject about which we have never learned very much, and neither have our sciences. Such questions will be answered in time, but it will just prolong the wait if we keep using pseudo-explanation words like holistic and gestalt. True, sometimes giving names to things can help by leading us to focus on some mystery. It's harmful, though, when naming leads the mind to think that names alone bring meaning close. 2.4. Wholes and Parts. A quote from Percy Shelley. It has been the persuasion of an immense majority of human beings that sensibility and thought, as distinguished from matter, are, in their own nature, less susceptible of division and decay, and that, when the body is resolved into its elements, the principle which animated it will remain perpetual and unchanged. However, it is probable that what we call thought is not an actual being, but no more than the relation between certain parts of that infinitely varied mass, of which the rest of the universe is composed, and which ceases to exist as soon as those parts change their position with respect to each other. What is life? One dissects a body but finds no life inside. What is mind? One dissects a brain but finds no mind therein. Are life and mind so much more than the sum of their parts that it is useless to search for them? To answer that, consider this parody of a conversation between a holist and an ordinary citizen. Holist: I'll prove no box can hold a mouse. A box is made by nailing 6 boards together, but it's obvious that no box can hold a mouse unless it has some mouse tightness or containment. Now, no single board contains any containment, since the mouse can just walk away from it, and if there is no containment in one board, there can't be in any 6 boards. So the box can have no mouse tightness at all. Theoretically, then, the mouse can escape. Citizen: Amazing. Then what does keep a mouse in a box? Holist: Oh, simple. Even though it has no real mouse tightness, a good box can simulate it so well that the mouse is fooled and can't figure out how to escape. What then keeps the mouse confined? Of course, it is the way a box prevents motion in all directions, because each board bars escape in a certain direction. The left side keeps the mouse from going left, the right from going right, the top keeps it from leaping out, and so on. The secret of a box is simply in how the boards are arranged to prevent motion in all directions. That's what containing means. So it's silly to expect any separate board by itself to contain any containment, even though each contributes to the containing. It is like the cards of a straight flush in poker. Only the full hand has any value at all. The same applies to words like life and mind. It is foolish to use these words for describing the smallest components of living things, because these words were invented to describe how larger assemblies interact. Like boxing in, words like living and thinking are useful for describing phenomena that result from certain combinations of relationships. The reason box seems non-mysterious is that everyone understands how the boards of a well-made box interact to prevent motion in any direction. In fact, the word life has already lost most of its mystery, at least for modern biologists, because they understand so many of the important interactions among the chemicals in cells. But mind still holds its mystery, because we still know so little about how mental agents interact to accomplish all the things they do. 2.5. Easy things are hard. In the late 1960s, Builder was embodied in the form of a computer program at the MIT Artificial Intelligence Laboratory. Both my collaborator Seymour Papert, and I long desired to build a mechanical hand, a television eye, and a computer into a robot that could build with children's building blocks. It took several years for us and our students to develop Move, See, Grasp, and hundreds of other little programs that we needed to make a working builder agency. I like to think that this project gave us glimpses of what happens inside certain parts of children's minds when they learn to play with simple toys. The project left us wondering if even 1,000 micro skills would be enough to enable a child to fill a pail with sand. It was this body of experience, more than anything we'd learned about psychology, that led us to many ideas about societies of mind. To do those first experiments, we had to build a mechanical hand equipped with sensors for pressure and touch at its fingertips. Then we had to interface a television camera with our computer and write programs with which that eye could discern the edges of the building blocks. It also had to recognize the hand itself. When those programs didn't work so well, we added more programs that used the finger's feeling sense to verify that things were where they visually seemed to be. Yet other programs were needed to enable the computer to move the hand from place to place while using the eye to see that there was nothing in its way. We also had to write higher-level programs that the robot could use for planning what to do, and still more programs to make sure that those plans were actually carried out. To make this all work reliably, we needed programs to verify at every step, again by using eye and hand, that what had been planned inside the mind did actually take place outside, or else to correct the mistakes that occurred. In attempting to make our robot work, we found that many everyday problems were much more complicated than the sorts of problems, puzzles, and games adults consider hard. At every point in that world of blocks, when we were forced to look more carefully than usual, we found an unexpected universe of complications. Consider just the seemingly simple problem of not reusing blocks already built into the tower. To a person, this seems simple common sense. Don't use an object to satisfy a new goal if that object is already involved in accomplishing a prior goal. No one knows exactly how human minds do this. Clearly, we learn from experience to recognize the situations in which difficulties are likely to occur, and when we're older, we learn to plan ahead and avoid such conflicts. But since we cannot be sure what will work, we must learn policies for dealing with uncertainty, which strategies are best to try, and which will avoid the worst mistakes. Thousands and perhaps millions of little processes must be involved in how we anticipate, imagine, plan, predict, and prevent. And yet all this proceeds so automatically that we regard it as ordinary common sense. But if thinking is so complicated, what makes it seem so simple? At first, it may seem incredible that our minds could use such intricate machinery and yet be unaware of it. In general, we're least aware of what our minds do best. It's mainly when other systems start to fail that we engage the special agencies involved with what we call consciousness. Accordingly, we're more aware of simple processes that don't work well than of complex ones that work flawlessly. This means that we cannot trust our offhand judgments about which of the things we do are simple and which require complicated machinery. Most times, each portion of the mind can only sense how quietly the other portions do their jobs. 2.6. Are people machines? Many people feel offended when their minds are likened to computer programs or machines. We've seen how a simple tower building skill can be composed of smaller parts, but could anything like a real mind be made of stuff so trivial? Ridiculous, most people say. I certainly don't feel like a machine. But if you're not a machine, what makes you an authority on what it feels like to be a machine? A person might reply. I think, therefore I know how the mind works. But that would be suspiciously like saying, I drive my car, therefore I know how its engine works. Knowing how to use something is not the same as knowing how it works. But everyone knows that machines can behave only in lifeless mechanical ways. This objection seems more reasonable. Indeed, a person ought to feel offended at being likened to any trivial machine, but it seems to me that the word machine is getting to be out of date. For centuries, words like mechanical made us think of simple devices like pulleys, levers, locomotives, and typewriters. The word computer-like inherited a similar sense of pettiness, of doing dull arithmetic by little steps. But we ought to recognize that we're still in an early era of machines, with virtually no idea of what they may become. What if some visitor from Mars had come 1 billion years ago to judge the fate of earthly life from watching clumps of cells that hadn't even learned to crawl? In the same way, we cannot grasp the range of what machines may do in the future from seeing what's on the view right now. Our first intuitions about computers came from experiences with the machines in the 1940s, which contained only thousands of parts. But a human brain contains billions of cells, each one complicated by itself and connected to many thousands of others. Present-day computers represent an intermediate degree of complexity. They now have millions of parts, and people already are building billion-part computers for research on artificial intelligence. And yet, in spite of what is happening, we continue to use old words as though there had been no change at all. We need to adapt our attitudes to phenomena that work on scales never before conceived. The term machine no longer takes us far enough. But rhetoric won't settle anything. Let's put these arguments aside and try instead to understand what the vast unknown mechanisms of the brain may do. Then we'll find more self-respect in knowing what wonderful machines we are.